Hello everyone, and welcome to a little pre-lecture video about ranking acid. For this video, we're going to focus on the factors of how you're going to make the comparisons, and then in class we'll talk about the actual skill of ranking the acids and how you'll actually apply them. But your book actually talks a little bit about this. I just want to make sure that everyone's really clear on the different factors, so that way when we get into class you won't be stumped. So first off, I do want to mention that there's another way that you can compare acidity, and this is one that we'll actually use in class. We're going to use the pKa sometimes. So the pKa is a measure of the equilibrium for acid equation, as you can see here. The acid equation is what happens when you put an acid in water. What should happen is if it's an acid, it should deprotonate, right? So the acid should act as an acid, and then the water would act as a base. And then you would get a conjugate base of whatever that acid was, and H3O plus, which is the conjugate acid of water. So basically all that means is the acid's acting like an acid and donating a proton, and how willing is it to do that? If you're not really familiar with equilibrium, we can talk about it a little bit later, but for right now, all you have to know is it's just the reaction can go forwards and backwards, and there's some sort of balance. And what we care about is where the equilibrium lies. Is there going to be more products favored, meaning you get mostly product, or is there going to be more reactants favored, meaning the reaction's not really working, it's not going forward? So that's what we're going to talk about. So if you have a pKa, what you need to know is that a low pKa is actually a good thing. It means that the product is favored and there's more of the acid in the conjugate base form. So the acid's acting like a good acid and making a whole bunch of conjugate base. In a high pKa, that's actually not good for acids. That means that the reactants are favored, and that's not what you want. That means the acid is mostly staying in the acid form and not donating the proton like you would want it to do. So that would be a weaker acid. So for this class, I'm going to give you some of the pKa's that you need to know, and those are going to be given in the activity section 1 folder. There's an activity called pKa's to know. So that way you know which ones I expect you to know, all right? And then we can talk in class about whether or not you have to memorize all of those or just some of those. We can talk about that. But those are the ones you'll have to work with. So you want to make sure that you do that activity so you know what the conjugate base of each of those acids look like. So knowing the pKa is great, but what if you don't have it memorized, or what if you come across a new molecule? We need another way that we can figure out how acidic something might be compared to something else. So we're going to use these things I call the 5 factors. These are factors relating to chemistry and stability that we're actually going to use throughout the whole course. We're just going to focus on using them with acids and bases right now, and we've already actually talked about some of these. So the 5 factors that we care about are electronegativity, size of the atom, resonance, hybridization, and inductive effects. So we've actually talked about 4 out of these 5 things and their existence, but we're going to talk about them and how they relate to acids and bases now. So before I get into detail about that, I want to talk just for a minute about what this even means. Basically, if we're saying that this is the reaction going forward, if you have a product that's more stable than the reactant, that's a good thing. That means a reaction will go forward. This is the abbreviation for reaction. Just if you haven't seen it before, you're going to see it a lot, so that's just a quick way to write that. All right, so basically what we're talking about is reactions tend to go from higher energy to lower energy, so from less stable to more stable. So lower energy actually means that something's more stable because it has less potential to do some stuff. The way I always think of this is whenever I have low energy, I'm like stuck on the couch just laying down, I'm not going to do anything. I'm not doing anything exciting, no reactions for me. Whenever I'm high energy, I'm jumping around doing stuff, I'm more likely to do something that's going to change something, right? So high energy is more reactive, low energy is more stable. And that's what molecules want to be. That's their dream. So then if we're trying to make something that's more stable, we obviously want the product to be the more stable thing. That's what we're working towards. So the more stable the conjugate base, that means you have a stronger acid. So that means the better it is at being an acid, right? The more likely it is to donate that H+, so that hopefully makes sense. So with that information in hand, let's talk about how we're going to rank the 5 factors and what we're ranking. What we're actually going to be ranking is the stability of the conjugate base. So we actually want the conjugate base to be more stable, and that's what these effects are going to have. So as you might imagine, if we're losing an H+, the conjugate base is usually going to be a negative charge. That's not always the case, but it's often the case. So usually that's what we're going to be comparing. If we had something where the conjugate base was neutral, that means we'd have a positive charge in the acid, and you can compare things that way, but it's just a little switch around with the effects. So we'll mainly focus on what stabilizes a negative charge, but we can talk about positive charge when we need to. All right, so let's start with electronegativity. So this is the effect that you would use if you were comparing two acids and they had everything similar except for one element, and the elements were different by being across the row on the periodic table. So this would be like carbon versus nitrogen versus oxygen is a common one. So if you're going across the row, we already mentioned that electronegativity is a big factor before, right? So that's a good thing. The size is not as big a deal. So because the sizes are similar, that's what matters, is electronegativity. The more electronegative the atom is, the more it is likely to stabilize a negative charge. So that's a good thing. So if we're looking conversely on the size of the atom, so let's say we're going down the periodic table, everything's the same except for we're going down the periodic table, and the thing with the charge is a different sized atom. So this might be like oxygen versus sulfur. They're in the same column, not in the same row. So now the size is different, and because the size is different, actually van der Waals plays a much bigger role because it's a whole extra electron shell bigger. So because you have that extra size, that actually makes it more stable because it's something called polarizable. The bigger an atom is, the more it can spread out its electrons. And remember we said delocalized electrons are good? It's not totally moving them to a different atom, but it's just sort of squishing them around in the electron cloud. So the more they can sort of mush around. So that's a good thing for big atoms that they can do that, and it stabilizes them. So even if they have a negative charge and they're more squishable or polarizable, that means they're bigger. That's a good thing, it's more stable. So in that case, the larger atom, the one that's further down, would be the more stable. When you're talking about resonance, the more structures you have, the more stable it is. So if you form a negative charge for the conjugate base, and that negative charge can then be delocalized, like we showed before in resonance, that's actually really great for the molecule, because the more structures it has, the better off it's going to be. So more resonance equals more stable. So anything that has resonance versus not having resonance, the resonance would be better. For hybridization, we talked about this a little bit based on the electron domain, so hopefully you can identify that. But what we didn't mention is that it actually has an effect on charge stability as well. So the more stable things are, sp is the most stable for a negative charge, then sp2 and sp3. The reason for that is because an sp hybridized orbital is half p and half s, right? Just by if you look at the numbers. So the s is actually the one that's more stabilizing for a negative charge because it's a sphere. All the electrons are close to the nucleus, which is the positive charge, and that's actually really great for them. If you're in a p orbital, you'd actually be in the dumbbell, and the dumbbell has this space in the middle of the dumbbell where it's actually there's no electrons can be there. So that's actually not as stable for a negative charge. So the more percent s you have, the more stable it is. So sp is half and half. sp2 would be a third s. That's only 33%. That's less. And for sp3, it's actually 25% s. So if you just want to memorize the order, that's fine. But the reason is because the more percent s you have hybridization, the closer it is to the nucleus and the more stabilized a negative charge would be. So then the last thing we have is something called inductive effects. There's a little chart that I like to have here on the right, so we're probably going to want to memorize that. I'll talk you through it, but that's going to be something that's really important. So let's talk about that in a little bit more detail. So let's talk a little bit more about inductive effects. So far, all the effects we were talking about before had to do with where the negative charge was, like that atom in particular where the negative charge was or where the charge was. But what we're going to talk about for an inductive effect is when something that's not where the charge is actually has an effect even though it's not touching it. So inductive just means that an atom near the atom with the charge has some sort of effect on it. And some books will call this a substituent effect. A substituent means something attached, so it just means something attached to the thing with the charge. So if you look at the chart on the right, these are the different things we're going to look for nearby. So let's say we have a negative charge on, say, a carbon, but then nearby there's an oxygen or a nitrogen over here. This is an electron donating effect. ED stands for electron donating. So as you know, oxygens and nitrogens have lone pairs. They can actually push some of their electron densities, just sort of lean it to the side, not actually move it like resonance, but just lean it to the side and push closer to through that bond to another atom, and they sort of mush it to the side. So they cause everything to sort of slide. Now, that's actually a good thing for if you're a positive charge, but that's a terrible thing if you're a negative charge. And because we're talking about conjugate bases, we care about negative charges. So if I already have a negative charge and then you're leaning in with your negative charge, I don't like that. We're going to repel each other. So electron donating is actually bad for a negative charge. The reverse effect is called electron withdrawing. It's when you actually pull electrons away. Generally, this is for things where their electronegativity is more important than their lone pairs. So even though halogens have lone pairs, this is just how they behave. We've proven it experimentally. I can't explain why it happens. It's just nature, but it's true. So halogens actually pull electrons away. If you're a negative charge, that's great for you. So you're leaning away now from being stuck on the atom. You're like almost delocalized, but not quite. That's actually good for you. You're spreading out the charges again. So it'll pull you a little bit, and that's nice for you. So it's good for a negative charge. Again, if you had a positive charge, that'd actually be a bad thing. So if you have something that already has a positive charge, electron withdrawing is not good. So let's say you have two molecules and they have different inductive effects. So one's electron donating, one's electron withdrawing. Then all you do is just say, obviously, one's good, one's bad. Or if you have one that's doesn't have an effect, then it would be right in the middle, right? So no effect would be in the middle. So that's one easy way to rank them. But you can also have two that may have the same effect. Like if you have two that have electron donating, well, then it's going to matter how close is that electron donating effect to the charge. And also it's going to matter how many of those atoms do you have. So let's say I have one where there's an oxygen that's 2 atoms away and one where there's an oxygen that's 3 atoms away. The closer one's going to have a stronger effect, and if that's a bad effect for negative charge, that means it would be the less stable conjugate base. I could also look at the number. So let's say I had a chlorine nearby on one of my negative charges. And then in a different molecule, I had 2 chlorines nearby in the same distance. Then obviously 2 chlorines would be even better because that's going to compound the effect, and that would be good for a negative charge. So the 2 chlorine one would be better than just one. So you can actually change the effects if you see something where they look like a tie. That's how you would do a tiebreaker. So I know that sounds kind of weird, but we can definitely talk more about this, and there'll be lots of examples that you can try in your book and in the practice. All right, so that's pretty much all the factors that we need to know. Hopefully this was helpful. Again, I know the book said it, but sometimes it helps to hear it in a different way or think about it a little bit more. If you have any questions, you can definitely ask me in class, and then we'll be ready in class to apply all these different skills. So hopefully you'll feel ready for that. Talk to you soon. Bye.